So our topic is quasi-harmonic equation for axisymmetric problems. So here we'll be using axisymmetric elements or ring elements, and we'll be discussing on three-noded ring elements. We will confine ourselves to three-noded ring elements. So axisymmetric means it's not dependent on theta. So when can we consider a problem to be axisymmetric? So these are the conditions, required conditions. So geometry has to be axisymmetric, material property has to be axisymmetric, the right hand side, that means F, which we have seen in our quasi-harmonic equation in 2 dimension and 3 dimension. The F, that right hand side, has to be axisymmetric, and the boundary conditions also have to be axisymmetric. So if these conditions are satisfied, then the field variable phi is actually a function of r and z only, and it is independent of theta. That is del phi del theta is equal to 0. So here you see one axisymmetric solid. Actually we have only shown half of it. Actually it is a full 360-degree axisymmetric solid or solid of revolution. Here we are showing this cross section, and we have discretized this cross section using three-noded triangular elements. See, they're all three-noded triangular elements. So now, as phi is not dependent on theta, we have not made any discretization in the theta direction. So actually this triangular element is a solid of revolution, This triangular element is actually a solid of revolution, like this, and the cross section is actually this triangle. So if you take an infinitesimal area DAE here, this triangular element is shown here again in a larger size. So this infinitesimal element also, if you rotate this infinitesimal element, this is the top surface. So if you rotate and rotate it 360-degree, then this becomes again a solid with infinitesimal cross-sectional area. And anywhere, this is actually, if you go d theta in the theta direction and take this becomes d omega e. So d omega is DAE into r d theta. So this is r d theta, and this cross section is DAE. So this volume is r d theta into DAE. This is DAE into r. Sorry, this is DAE. This is DAE into r d theta, and DAE means dx dz. So this is r dx dz d theta. So, and if you assume that this inner surface is a Cauchy boundary, then, and this is the edge, a portion of an infinitesimal portion of the edge, and then if you rotate this edge, then, and you take an element like this is actually a surface element ds2e, and this is the edge, not surface element, infinitesimal surface, and this is the infinitesimal edge. So this whole surface is s2e, this and sorry, so this whole surface is s2e, this whole surface is s2, this whole surface is s2, and this is for this element. So this whole surface is, whole circular surface is s2e, this is ds2e, and this is d gamma to e. This is capital gamma. So this is, so pardon me if I have told it tau. No, this is not tau. This is capital gamma to e. So now you can easily, this is the axisymmetric equation in 3 dimension, and you can easily convert it to axisymmetric case by using this transformation relations, that is Cartesian to cylindrical polar transformation. So del r is del x del r plus del y del r. So this is the chain rule of differentiation. You know del r and del theta. So in matrix notation it is like this. So this is this, and you invert this, then del x del y becomes this. So del x is this and del y is this, and here we assume that the kx and ky, in the kx and ky, that is in the plane perpendicular to the axis, the plane perpendicular to the axis, kx and ky are equal, and it is a function of r and z and not theta. So here this kx and ky we will replace by k, this kz will remain. So if that is so, then you just take this del x from here, put it here, and assume that del phi del theta is 0. So this term goes. So this becomes this, and this becomes this. So if you add this and this, you get this to be this. Now these first two terms, they can be combined to form a term like this, and this is actually the equation of quasi-harmonic equation in axisymmetric condition. And again the boundary condition, if you take the axis x y, this x r y theta is a plane perpendicular to z, and nr is along r direction, n theta is along theta direction. So this is nx or I is along x direction, and ny or j is along y direction. So if you just convert, if you take the transformation relation for vectors, so nr is nx cos theta, nr is nx cos theta plus ny sin theta. So you just take this component and take this component. So nr is nx cos theta plus ny sin theta. So in this way you form this, you replace it here, and again del x you replace from what you got earlier. So now you get this. Now if you add these two, then you get this as this. Again here you have to remember, that h is a function of r and z alone, and g is a function of r and z alone to make it axisymmetric, and kx has to be equal to ky, and that is k. So kx equal to ky equal to k, and that is a function of r and z alone. So now that we have got the governing differential equation for quasi-harmonic axisymmetric case along with the Cauchy boundary condition, the Dirichlet boundary condition is simple. It is only phi specified boundary. So now you when you derive the finite element equation using Galerkin's principle, you use the weighting function ni, and this is what you do. So d omega, as we have discussed already, is r dr d theta dz. Dr dz is dae, and r d theta is the length in the theta direction. So since nothing is dependent on theta, so theta direction can be integrated independently. So you make it twice pi, and this is this. So here you see this r we are using, and this r when it gets multiplied with this is gone, and here one r comes, and since this is del z, r goes inside. So this is kzr, because when you perform del z, then r is actually a constant to it. So this is what you get, and dr dz, as we have told, is dae. So that means this becomes similar to what we got in 2 dimension, only kx has been replaced by kr and ky has been replaced by kz into r, and f has been replaced by fr. Now as you know, this term when integrated over the area gives one domain term and one boundary term, and the boundary term is on gamma to e. So this term is this, so, and this goes over the boundary. So this gives you, when integrated over dae, this gives you this boundary term and this domain term. This is exactly similar to what we did in 2-dimensional case. So this is one boundary term, and from the second term another boundary term comes when you use Gauss divergence theorem. So now if you add, now when you add these two, this term and this term, like this, you add these two, and then this boundary terms also get added, and now you use the boundary condition, this. So you use this boundary condition. So this plus this is minus h phi minus g. So when you use that, then finally you get this equation. So here you see one r is multiplied, so with the boundary condition r will get multiplied, kr this, kzr this, plus h phi r or hr phi plus gr. So here in a finite element equation, here this term as usual, this term as usual, so this gives you the element stiffness, and this is the stiffness coming from the convective boundary, only h has to be replaced by hr. Now this is the forcing term from the domain, f has to be replaced by fr, and this is also the flux boundary part, so this g has to be replaced by gr. So this integration is on gamma to e, this integration is on gamma to e, because this is from the boundary, stiffness from the boundary, force from the boundary, force or vector from the boundary, vector from the domain. So now how do you evaluate this? So you do B transpose dB. So here actually the problem is this, here one r comes, and this r is not constant over the area, but to bypass this problem, what we do, we in place of r, we take the r value, we consider r to be constant, and that r is the r of the centroid of the area. So this makes the calculation simple. So our philosophy while using triangular elements is this, is to keep the things simple, and in order to keep the things simple, you just increase the number of elements, make the element size small, and neglect the variation of r within the element, and replace the r by the centroidal r, so that you don't have to integrate. So this is the stiffness from the boundary due to the convective term. I think I have missed one h here, so here please introduce one h. Here there will be one h which I have missed, so please introduce one h here, and this is the fourth term, and this is the final equation which we are getting. So this completes our discussion on quasi-harmonic axisymmetric equations using triangular ring element. That means the cross section of the ring element is triangle with 3 nodes. So thank you. So let me stop here.